I'll kill this guy right here. Okay. All right. Yes. I think we're ready, so I'll just start it, Carol, even if I'm jibber-jabber. And then, okay, don't forget, if they can't, make sure you're standing right over here. Okay. So I need to stand in front of the mic? Yes. I'm just because sometimes it's hard to hear on the WebEx. Hi, good afternoon, everyone. Thank you so much for coming out to today's seminar. I would like to start by thanking the Washington Statistical Society and the Bureau of Labor Statistics for organizing and hosting this seminar. So a few introductory items to address. If you have not already signed in sign-in sheet, we have sign-in sheets in the back of the room. We also have a couple of handouts for you. One handout contains files that are referenced in today's talk, and then there's also another couple of handouts if you're interested or if you haven't already joined the ASA or the Washington Statistical Society. We would highly encourage you to do so. Those of you that are not in the room, that are dialed in remotely, please feel free to send an email to Carol Bloomberg if you're interested in or any of today's handouts at cbloomberg@gmail.com. Yep. Yeah. And for today's structure, for the first hour, David Marchette is going to give his seminar, and after that, we're going to open it up to questions from the audience. And if you are dialing in, you can't speak into it. We've had you, so you're going to have to enter the question in the box, but we'll be able to see your questions there. I'll take questions for about 20 minutes. They'll take us until about 5:30. Afterwards, we're going to have a reception at East Street Cafe, in which everyone will pay for their own food and beverage. And yeah, that's it. And, so a few notes about Dave. He's a principal scientist at Naval Surface Warfare Center, responsible for leading basic and applied research projects in computational statistics, graph theory, work analysis, pattern recognition, computer intrusion detection, and text analysis. He received a PhD in computational sciences and informatics from George Mason University, and also a bachelor's and master's degree in mathematics from the University of California, San Diego. He's a fellow of the American Statistical Association and the American Association for the Advancement of Science, and an elected member of the International Statistical Institute. So here I will let Dave take over.
Okay, thank you very much. And thanks for inviting me. I am going to, first I'm going to share the thing. Oh, I have to make the recorder go away. Oh, there it goes. Okay. All right. So I'm going to give an intro, some discussion about network data, various other topics. These that I'm going to be talking about here is going to be either very simple or it's going to be hints towards things that are more complicated. And for many of you, these topics will be things you've seen before. It might be from a slightly different perspective than you're used to. But I'd like to introduce some novel techniques and ideas, still at a very simple level, because I'm a very simple person. It's really easy for me to understand simple things. And so I'll go through a lot of interesting simple things, and I'm going to talk about how these simple things are applied in a couple of computer security type problems and computer security depth. So as I said, I'm a very simple guy. I like simple. And simple is extremely powerful. As you'll see, there are some really basic, simple ideas that are just useful and powerful. And what I've learned is that complicated things are only complicated until you understand them, and they become simple. So some of the things that I think are really simple, you may say, but we can chat about that, and by the time we're done, I think you'll think they're simple too. Talk about some cybersecurity data. I'll discuss some network data and some malware data. and then we'll look at a couple of what I consider to be basic statistics techniques, kernel estimators, and some discussion on streaming data, and we'll look at machine learning. Network data that I'm going to talk about is mostly network flow data. So you know, Senator Ted Stevens famously said the internet is not something that you just dump something on. It's not a big truck. It's a series of tubes. And that's true of network flows. Network flows are the tubes. You think of these as when I connect to a web server to get web pages, I get a flow in one direction. Everything I type to the web server or click on or whatever goes there. There's flow coming back, which is everything the web server is sending me. So those two flows are connected logically in that both of them happen transparently to me to see and select the things that I'm downloading or that I'm looking at. But from a network flow perspective, they are two different flows. Maybe far more than two, actually. Sometimes images get their own flows, all kinds of things happen. But we're going to look at these flows, and the flows consist of packets. So every command you give or every image you see or every web page you see is broken up into little chunks, randomly out into the network, and it's a complicated situation, but you can think of it as just they're thrown out into the network and somehow they find themselves to me and they get all put together again. And flows track of is how many packets and how data and how the flow is open. So, there are a couple of other things you need to know about that happen with these flows. There are two IP addresses. These are the main addresses. It's 4 bytes of 4-byte integers, but it's really I say 16-bit integers. It's actually 30-bit. That's a typo on my part. And that is a unique identifier for your computer or for the server. In addition to that, there are these things called ports. The ports are the 16-bit integers. I guess I was wrong. I thought I was talking about IP addresses there. It's ports. They are 16-bit integers. You can think of them as Ted Stevens's tubes. So a computer has a port associated with my flow. Everything that goes out of that port to the port of the other computer, all of that, the machines know belong to me. And so all that goes to me. Somebody else is on my computer and is going out. They get a different source port. The destination port tells what application you're going to. So, for example, if you're going to web, the destination port is most likely going to be either port 80 or port 443. 443 is the serial web. The source port generally doesn't mean anything. It's just a random number that is assigned to your flow so that you can get your stuff. So all the packets get transferred back and forth, and the flow keeps track of how many packets and how much data. And as I said, if two people are using the computer at the same time, they each get different ports, and so the computer knows who gets what stuff. So there's some good data at Lionel. They have network flows, a lot of data. They just put up a new data set that's something like 12 gigabytes compressed. So it's a huge data set. I don't have any idea. I haven't even looked at it. I have no idea how big it is as there's number of packets and things, number of flows. For the different fields in the data, there's time, which is how long the flow was in existence. Source destination IPs are in this data, they've been obfuscated. They've been just turned to things like computer 1, computer 2, that kind of thing. And the source and destination ports, some of them have also been obfuscated, but the common ones ones like 80 and 443 are left alone. So you can tell what application they're going to. Protocol is, there are a whole bunch of different protocols. You don't have to worry about that, and I'm not going to talk about that here. There's number of packets and number of bytes. So we'll look at number of packets and number of bytes. With a new data set, the first thing I do is take a look at it. How do you take a look at data? Well, as I said, we're going to look at number of packets and number of bytes, so that sort of says we should do a scatter plot. My mantra is simple is better, so let's just look at simple plots. So essential scatter plot, the simplest thing we can do, we'll plot the number of packets against the number of bytes. Think about this for a minute. This is an application where I'm sending some packets out to somebody and I'm getting stuff back. And that packet is got a chunk of the thing getting back. So logically, you should fill that packet with as many bytes as you can. Right? Why send 100 packets if you can just send 3? Right? So logically, you might think that every packet is going to be full, except maybe ones at the end where you're done. So what you have to see is number of packets is a constant multiple of number of bytes, or versa. So that's what we expect to see. And that's what we see. A little bit hard to see, but you can see there's more than one diagonal line here. And it's a little, there's a little bit of extra line down there near the big glob of junk. And if you pick up to the screen and put your face right up against it, you would see maybe 2 lines on that diagonal thing. And so that little line down on the bottom. The x-axis is number of packets, the y-axis is number of bytes. Why are there these weird things? Why aren't we seeing what we should see, which is one diagonal line with maybe a few little scattered things for things that didn't have very much data? And the reason for this, there's a couple of reasons. One reason is think about the web traffic. On a web page, what am I sending to the web page? Sending the web page. How big is that? How big the URL for the web page is, it's probably not very big. Sending back everything on the web page. So they're going to try to fill the bytes. So C is at a minimum 2 different lines with different slopes because we have these 2 processes. Now think about, I don't know if you guys are old enough to know about terminals into computers. Now that people are starting to go to servers, a lot of places are having you log on to a server to do your stuff. Well, every time you touch a character on the keyboard, it gets sent. Every packet has basically 1 bit in it going one direction because they want to get that over there as fast as possible, fast as you can. Because if you do something important, that says send me stuff, you don't want to wait while it thinks about it. You want the system over there to know it instantly and start sending. So there you see a lot of packets that only have 1 byte or maybe 2 bytes. And so there are a whole bunch of variations on this thing. So this very, very simple plot has told us a lot about our data that we hadn't known up to now. So here's another simple plot. This one is a little less simple. All I've done is converted it to polar coordinates, right? We had those lines. So instead of looking at the lines, let's look at theta and r. And those lines should be vertical lines. So you see a bunch of other interesting things in this plot. Notice down along the bottom, we see all of those sort of curves, and there's some plot effects. That's the discretization of data. Things are number of packets and number of bytes. There's the discretization going on, and we see that in the data. We also see a lot of interesting structure over on the right there, little groups and globs and all kinds of interesting things. I idea what that is. So that would be interesting to look at. Look at those, what's going on. Are they particular applications? What's going on with that? So just from a couple of very simple plots, you see a lot of structure in this data. Now, unfortunately, we're not going to see any in the data because the data does not come labeled with a, and I haven't gone through to find them. I have some things to look for, but I just haven't gone through. So, as I said, the interactive flows like terminals, SH, Telnet, nobody uses Telnet anymore, but those kinds of things tend to send packets that have a single character at a time. And then what comes back is whatever would go to the screen, and it comes at a big block. So if you type ls and the Linux terminal, it's going to give you all the files in the directory. So it's going to send you all of it in one. Well, data transfers, like if you're watching movies on YouTube, or you're getting images, or whatever, those tend to fill packets as full as they can and send them out as fast as they can. Also, I mentioned the protocol flag. These tend to use different protocols, because different protocols can be faster. And that's another thing you can use to understand what's going on. As the different lines, or the different vertical bars in the polar coordinates, they indicate different applications or different ends of the flow. So what might you want to do if you're looking at this network, if this is your network, see something on a port that you don't expect the network to be open, you can look at the node and determine, is this of type web, or of type FTP, or whatever, assuming you do the analysis on these both normal. So the idea is you look for unusual patterns on your brand new ports where you don't know what's going on, or on existing ports where they should act a certain way, but they're acting differently. You might see that some is exfiltrating a lot of data out on a port. Or you might see, you can look at these things in time. Should be a lot of activity on your network at night. Well, if you're in a university, maybe you should expect that. But if you're in a business, maybe you shouldn't. And there's a lot of patterns like that that you can look at these flows and do the analysis. So look at some very basic just understand the distribution of the data. What does that mean? Well, for statisticians, that means I want to know what the probability mass function, the probability distribution function is. I want to know the model that I should be applying to this, that should be fitting to this. Well, I have no idea. How am I going to guess what model to use for these flows? I'm going to have to start looking at the flows and see what they look like. So let's look at the flows and see what they look like. Everybody knows the histogram. That's going to be the starting point. So we're going to histogram of things. So with histogram, you set out a set of bins. We're going to do one-dimensional histograms today. You set the bins and count each thing that goes in each bin, and maybe divide by n if you're doing the frequency. So the histogram of some data. Look at that and we see, well, okay, it's obvious that there's a bump on right around 1, and maybe there's a bump just to the left of 0. Okay, cool. So now we know something about our data. What's the bin? Exact same plot, same data. I just shifted the bins a little bit. Now, bump down 0 is not at all obvious. All right, this is a well-known feature of histograms. If you change where the bins are, that changes where the points lie, and you can get very different pictures. And of course, we can increase the number of bins. Another picture, that little bump is showing up better. There are rules of thumb for picking the number of bins. I don't have a problem with that. But this shifting where the bins are worries me. I don't like that. It's for just being a, an idea of the data, but I don't like that. So, of the kernel estimator. So I'm going to think about a histogram a little bit differently than maybe we're taught in school. In thinking, I'm putting the bins down and I'm going to count how many points are in it. I've got a little block for each point, and I'm going to put that block over each bin every time I see a point. So I stack up these blocks in the middle picture. Think about that. Why did we center those blocks on the bin? What centered the block on the point it corresponds to? Now, the picture on the right isn't quite right because I dropped the blocks down the way I'm supposed to. But if you do that, you get a whole bunch of lines. You can't see what's going on. So the idea is those blocks are centered over the point. We're going to drop them down and we're going to add them all up. Well, with blocks, it's kind of hard to see, so let's put bumps. So I'm putting a bump on every point. Okay, that bump, it turns out, is a Gaussian, but a normal distribution, but you can put pretty much anything. And I add them up, and I get that smooth version that we see there. That's the sum of those bumps. Okay, there are no bin positions here. The only parameter we have to adjust other than deciding what kind of bump we're going to put is the width of the bump. Okay? So we eliminated one parameter. That's nice. Thing is, if we use smooth bumps, we get smooth pictures. And that's also kind of nice. It can be bad, but for most of what I like, that's a pretty good thing. So in math, take some kernel. That's your bump. Kernel, that function can be anything. Well, it can't be just anything. We get to integrate to 1 because we want a density out of this thing. We like it to be positive, although that is actually required. But we handle that differently. So we'd like it to be positive. So we get density, in other words. And technical reasons, we'd like it to finite variance and to be centered at 0. It's dumb if it's not centered at 0, right? Because you're going to center it on those points. Also, it should be unimodal, otherwise that's dumb. If I point down for every point 2 bumps, what the heck am I going to get out? I have no way of interpreting it. So what we really want, we want those bumps. We want a Gaussian or a circle. We want a bump. A bump. Okay, so there it is. It's just a sum of these things divided by n. And it's got this thing h, which is called the bandwidth. You can see it as the width of the bin, or you can think of it as the standard deviation of your bump. It's the width of the bump in some way. This is just an average. We're averaging these over, and we'll come back to that in a minute, which is cool, because averages are simple. I understand averages, so that's good. It's a measure of normals. A measure of normals is just a weighted average of normals. Your lengths are 1 over n, and it's kind of stupid. But that's another thing that I will probably mention when I'm dead. Data, again, network flows. There it is in the coordinates, or not parallel coordinates, sorry, polar coordinates. And down below is my univariate estimator of just the theta, just down to the x-axis or the axis. All bumps correspond to lines up at the top. Okay, kind of cool. You can go through and you can do bump hunting, and there's a whole bunch. So kernel estimators are very, very simple. Now we can get complicated if we want. I'm going to go through the details of this, but that bandwidth controls how smooth this thing is. It controls how many bumps there are. There's a lot of work that's been done where you either change the bandwidth and see how the bumps get affected, and that tells you which bumps are real or real at various scales. And there's also work where you have different bandwidths in different regions. You notice on the right there's a lot of dark, so there's data on the right. On the left, it's not as dark, it's much sparser. Maybe we want larger bandwidths on the left than the right, so we can play around with those things. So very simple idea, and now we've looked at ideas for making it more complicated. The thing I want to mention is that I always use normal distributions. And really good, well, there's moderately good reason why I shouldn't. That is, they have infinite tails. You know your data doesn't live outside of certain ranges. That's a problem. So again, we can get a little more complicated. There are ways to correct if you know where the edges are. And there are non-infinite tail densities you can use. Computer security, as I said, the LANL data, the new LANL data is gigabytes and gigabytes of hundreds of thousands, I think, of flows. So huge amounts of data, and it typically is coming very fast. If you're looking at individual packets and saying something about them, you're going to see hundreds of thousands, millions everywhere on networks in the world. It's much higher than that on some networks. And so if you're looking at a whole network, you're going to see you're going to see thousands of things a second. If you're looking at a major mail server, you're going to see thousands of emails, hour, day, whatever your time scale is. Virus scanners, if you've had the pleasure of having a virus scanner mandated to you on your system, where it has to scan every single file on your system, there are zillions of files on your system. It can take a long time to scan through files. Every computer you have is logging stuff constantly. Everything you do gets logged in some way or another. So you use big, long log files. Sometimes we can't store all that data, either because we can't afford the disk or because we're not supposed to because of privacy issues, things like that. And if I want to answer a question about what's going on right now, I don't have to look back 3 years to see what normal was like to see if now is abnormal. We'd like to update our models in real time, is what I'm coming at. Okay, streaming data is the stuff that comes in real time. It's too fast to process. We can only store a small window of the data at any one time, or we'll assume we do that. We need ways to process the streaming data. Averages, kernel estimators and averages, so that's good. It turns out you can compute the average in real time, right? You don't have to do the sum over everything. If you've got the average for 100 million points and somebody gives you a new point, you add up those 100 million points again, right? You just multiply what you got by 100 million, add the and then divide by 100 million plus 1. Trivial, right? So we can compute averages online. Instead of multiply by n minus 1 over n for the average and 1 over n times the new point, if we just fix a value for that theta, just fix that implements an exponential window. It basically exponentially forgets the past, and so it likes taking just the current stuff, remembering just some of the past. So exponential exponential windows can be really useful in streaming. They focus on today. Today counts more than last week. But there is still a little bit of last week, and that's controlled by the value of theta. So we compute the kernel estimator the same way. It's just an average. We have to decide ahead of time where we're going to evaluate the kernel estimator in order to do this. But to do that, if we know we're going to ask for it at these points, then we can compute this in real time, streaming. What we can do is, I didn't say it in words, but we can do this multivariate too. We don't have to do univariate. We can use the multivariate kernel. So here is the log of the number of bytes, because it's a pretty picture. Time goes into the screen, and see a bunch of bumps that change in time. These are kernel estimators at each time. So that's kind of cool. A mixture of normals, as I said, that's just like the kernel estimator, except you only have m of them, and you can adjust the weight. And that, if you look here, that kind of looks like a mixture of normals changing time. All parameters in a mixture of normals can also be done in a streaming fashion. They're just averages too, and easy enough. The variance is a little hinky. You just have to do a little bit extra work to figure out what the formula is, but it's trivial. Now, fun stuff. The stuff really to do is machine learning, and the kind of machine learning I really like to do are the simple things that you get in the first couple of weeks of any machine learning class, plus the thing you get towards the end, which is also very simple. So to me, today, machine learning is going to be classification. There are other aspects of it, but today it's classification. What it is you've got some observations, some flows or packets or whatever, and somebody has labeled each one as being of some class, malicious or benign, an attack or not an attack, web traffic or secure shell, whatever the class labels are, and you can have as many class labels as you want. For today, everything has a unique class label, but there's things you can do. So we assume we've got some data for which we know what the answer is. So they've been labeled. Now this can be very tedious, this labeling. It can cost a lot of money. And so it requires people to do it. So what we'd like is an algorithm that'll give us new class labels on unlabeled data. We'd like that algorithm to be really good. So we need methods to build those algorithms. We'd like them to generally be very good. There is one that's kind of not too bad most of the time, and it's almost never really good. But still, it's trivial to implement. It is really easy. Also very simple to understand. It's a deal. Have your training data. You get an observation. You know, of training data, which point is closest to it? You class label for that point, and that's what you assign to your new observation. Trivial, easy to implement. Anybody can do it. It doesn't work too great, but it usually works okay. And you can get a little bit fancier. So suppose instead of just asking the nearest one, you say, give me the K nearest one. Give me the 7 closest points. And vote among them for the class label. You can assign it proportionally, right? If you're taking 7 nearest neighbors and 3 say it's red and 4 of them say it's blue, then it's 3/7 red, 4/7 blue. And so you can play tricks like that. They're not known about this, so for example, in the limit, the neighbor classifier is known to be no worse than twice the error that is the better you can get. So if the error you can get is 0.003, then this neighbor in the limit will be 0.006 or better. Okay? That's completely useless in real life, right? Because we're never in the asymptotic regime, or we have no idea whether we are. But it's good to know Turns out the K nearest neighbor is consistent. In the met, assuming you choose K slowly but not too slow, that will give you the best error. And from a practical standpoint, that's important to know and useful, but it's not going to really tell you much about your situation. So malware. Counts and examples of malware grouped by some human into 9 different families or 9 different classes. Problem. Class a piece of where it's from. So what they did is they dumped out the byte. We have numbers between 0 and 255 and every piece of malware. We have a whole bunch of these. So I'm just going to take the histogram, the frequency table, 0 to 255. That's going to be my set of features for this piece of malware. Okay? And when I tell computer scientists this, they laugh. This is stupid, right? It's going to work. So, but simple. And the idea was, I wasn't going to stop there, right? The idea was you start with 1 byte, then you get 2 bytes, and then because we're in pairs of 2 worlds, you go to 4 bytes, and you do feature selection as you go along. So this isn't supposed to be where I stop. Today, this is where I stop. We'll look at nearest neighbor classifiers. I think I actually look at non-nearest neighbor classifiers, but I've done so many things I don't actually remember, so you'll find out at the same time I do today. What I did is I just took 100 observations from each family to use as my training set. Okay, now 100 observations, this should just do terribly. There is one family that only has 42 observations, so it took 21 of that. Okay, so here is a 1 nearest neighbor performance. 54% correct classification on those 10,000 held test sets. That's crazy. That did not happen. Dumb feature. Okay? 98% if I split it 50-50. Okay? Use a 9 nearest neighbor class. What is going on? Why isn't this as dumb as I thought? Why does it work at all? As an analogy, the byte count histogram is analogous to the word count histogram that people use in text mining, text analysis. It's really hard to beat word histograms in text mining. People do it with these complicated topic models and stuff, but this is the simple idea that you get in text, which gets 90% of the way in text. That's just really more a morpheme count histogram or even a letter count histogram, right? Because nobody believes that the words are a byte. But still, the idea is intuitively a family shares code. Those bytes correspond to machines. They're parts of a machine instruction. What's a family if somebody takes a chunk of code and they modify it to give it some more functionality or to fool people or whatever? Don't mean it's not so dumb. So, I'm sure that the Kaggle that I just gave you is, and I think that might be okay. Here's a case where I'm a little bit worried about. So, instead of looking at the Kaggle data, let's look at viruses and phishing. And we're going to ask the question, can I tell if this piece of software is a virus or it's benign? And I'm going to do the same thing. Again, I'm going to say we'll start with bytes and we'll work our way up, right? But let's start with bytes and how well we do. I'm going to introduce a little bit more complicated classifier, but it's also simple. Calling them for it. This is the best classifier in the known universe. They're fluid. to argue with me. All the deep learning people, forget about them. They can do their deep learning stuff. And they're better than me on the type of data they're working on. But generally, random forest is the best thing you can have. Sort vector machines is also kind of comparable. You might have heard of that. But I like random forest. So idea. This is a cartoon version of what doctors do. You go to your doctor takes some measurements. Temperature is above this. Okay. Blood pressure is here. Okay. Now, I need to do this test, check to see the value of that test. And eventually the doctor says, you have the flu. Okay? So the doctor, in my cartoon view, is going down this tree where at each point he's looking at one observation and make a decision which side of the number is this observation. That idea, and instead of building the tree, it builds a whole boatload of trees. So there are a bunch of variations, but essentially you sample with replacement from the training data, build the tree. Then you do that a whole bunch of times. And you get a new observation, you trickle on all the trees. Now, trickling down trees is fast. It's just a bunch of if tests, right? So you pull it down all the trees, and at the leaf of each tree is a thing that says, well, this was pure red, or this was nearly pure blue, and so it tells you what class it thinks it is, and then vote among the trees. Really simple. They're hard to beat. There are some people who've done variations on random forests and shown, yeah, my data works a little bit better, but it's a very hard algorithm to beat. There's a really good paper by David Hand, which appeared in Statistical Science, which if you send me an email, I'll send it to you, which basically says, don't fool around trying to make better classifiers. You've got trouble than doing that. So, benign versus malicious. A whole bunch of Windows binaries and a whole bunch of bunch benign, a bunch malicious. We random forest and we get error. It's 9% accurate. And we're doing training tests. We're not cheating here. Okay? And okay, there's a little bit of a mismatch between benign and malicious. But and in a nearest neighbor, 88.9% accurate. Benign versus malicious. This is great, right? For the Navy. The Navy wants to put this on ships, right? Well, I don't want them to put it on ships, and I told them that because I believe it. I don't know what's going on. So there is something going on here. There is a difference. There is a difference between the benign data and the malicious data in terms of their byte count histogram. There is a difference. That difference, because of benignness or maliciousness, or is it some other factor? And I think I know the answer to that, which I'll tell you in just a minute. But here's some things to worry about. One is that we have just one set of data. How are you going to get computer viruses? You're going to go around asking people to give you computer viruses, right? You're going to go a bunch of places on the web. There are some repositories that have them. It turns out you can tell different repositories apart. Be a temporal thing. That might be we're telling, 2007 viruses from 2009 viruses. These are OS separated, so it's not an operating system. It's not Windows versus Linux, which you can tell. But it might be operating system version or something like that. Interestingly, if you build a classifier that on Linux for malicious and malware, and you build a classifier in Windows, malicious or malware, and you give each of them the other guy's stuff. Linux thinks all Windows files are malicious, and Windows thinks all Linux files are benign, which is amusing. Okay, so his story. Decided they were going to tell whether or not there was a tank, the kind that shoots, not the kind that you put water in. Pictures. So they collected a bunch of pictures of tanks, and then went out and they collected a bunch of pictures that didn't have tanks in them. They built a classifier. They did it right. They used test data, ran it through, got great results. Really did work well. And then they did the next thing you should always do. They went and got new data. It was a cost. They looked at their data. Always check your data, especially if you get performance that's better than you expect. Turn all the tanks. I mean, how do you get pictures of tanks? You go to an Army base and you say, "Can I take some pictures of the tank?" And they say, "Yes, but I'm not going to let you sit around here for 3 weeks. Do it today." And it was a cloudy day. Non-tanks, those you can go out anywhere and do anytime you want. They happen to go out on sunny days. What they had was a cloudy day detector. Okay? There was a difference between tanks and non-tanks. There were differences. What they cared about, there were tanks in it, wasn't what the classifier figured out. They used a neural network. You know, I'm picking on deep network stuff, but it didn't matter, and else probably would have done the same thing. So the day detector problem is what I think we've got here. So what I think is the answer to why this benign malicious thing seems to work so well. And it's the following fact. There is a thing called packing of your executable. The idea is twofold. One, you'd like to compress the byte. You know, 64-bit code, the stuff there are zeros. So you'd like to compress the executable files down. Some also want to encrypt it. Either it's malicious and you don't want somebody looking at it and finding that out, or proprietary and you don't want somebody decompiling it. And so there are a whole bunch of different packers, and people pack different chunks, different viruses that color. I think it's probably something to do with either the type of packers that are available at different times, or different families of malware use different packers than other. Benign uses different packers than malware, or the benign wasn't packed. Issues like that. I think it's a cloudy data. Know your data. Simple visualization. It's not important how pictures are made. They're made by a thing called TSE, and there's a site for it. But it provides a two-dimensional scatter plot for you. And on the left are the benign and the malicious, and you can see the benign things, the greens, are much different from the malicious, the red. Now this is a two-dimensional scatter plot, so obviously we've lost a lot of information, but they're clearly different. This says I classify these. It does not say I classify them because they're benign malicious that I'm keying on. It could be cloudy days still. The one on the right is the cow malware, by family, and from that it's pretty clear that cow malware is a duck. Another thing I'd like you to take away from this talk: never you do anything that has anything to do with randomness. Here's the first. I was playing around with the TSNE, and I happened to get this picture, and I said, "Ooh, look, that's a duck. I'll keep this." I've just been playing around, right? I didn't set the seed beforehand. I can reproduce that picture. And that's really sad. I tried pretty hard because that's a great picture. I have managed to get things to look kind of like dragons. So, I mean, it's not the end of the world. Also, I've taken up an awful lot of the hour here, but I just want to mention some stuff on manifold learning, which is a really cool idea. The idea is that you've high-dimensional data sitting around. You've collected some complicated data. It's got lots of features. You don't really believe it fills out all of this high-dimensional space. When we're looking at that stuff where we're looking at 250 or 256 features, we don't think it fills out all of 256 space. We think it lies on some kind of sub-manifold of the space. We'd like to find that. So, the ways to do that is build a graph, connect each point to neighbors, to things that are close to it, build this graph, and we do some complicated things, They're basic linear algebra. We compute eigenvectors is basically what we do. Or we compute distances on the thing, and we do this thing called multidimensional scaling, which is just computing eigenvectors of something. There are a couple of graphs. We can do an epsilon ball where we put a little ball of size epsilon around and connect everything. Or we can do a 3 nearest neighbor graph. Here's the basic steps. We can see a graph, nearness, and compute the eigenvectors of something. The adjacency matrix, the Laplacian of the adjacency matrix, distances, the shortest path distances. There's kinds of things, and different things will give you different features. We just compute those eigenvectors and use them. And here are some pictures of the Kaggle data. Here I've taken the graph and I've just laid it out, right? This is not something you do for inference because who the heck knows what the layout algorithm this particular thing used, right? This is sort of a default layout algorithm that a package gives me. So I can't really use that for inference because I don't know what the algorithm is. I figured that out. Here is one called the Laplacian. Here's another, which is the adjacency spectral embedding. The adjacency spectral embedding has the following property. If your graph is a block model, meaning that it's a random graph in which you are connected to another vertex based purely on which group you're in. So vertices have a group label associated with them, which you do not observe. And probability of an edge only depends on the group. So you think of them as little communities where you're likely to connect to your community than the others. If that's the case, adjacency spectral embedding will give you a mixture of normals. Pretty cool. Some normals are cool. I like them. And here using MDS, graph distance, which is a thing called isomap, which appear in science articles. They have this data called the Swiss roll, and they unroll it. And cool. But anyway. So, and a lot is known about these different embedding methods. I haven't really given them their due here, but it's very simple idea. It's compared by just looking locally at distances. Take that graph and you out a matrix, and now you do a linear algebra thing. Linear algebra may be a little complicated. If you haven't had it, then you don't know. But it's not. If you figure out what vectors what means, then it's pretty straightforward and it's pretty trivial. There's stuff that we can talk about, but we're hitting the end of the talk. So the final note is, I think there's lots of math that we can use for a lot of these different. I have been very, very biased towards very simple ideas, and it's been extremely extremely powerful and extremely successful for us. Which is good because when we start getting to the complicated, I get confused. A very
half an hour, I'm on my webinar.
That you might have heard about topological data analysis, a complicated way of operating those graphs, which comes down to being very simple once you understand it. But it starts the same way. You build a graph on the data, and then you compute these things which have to do with, having to do with how many holes are there. And it's a topological thing. If you haven't had algebraic topology, if you don't know what a homology is, don't worry about it, but that's where it comes from. And so the point, though, is that all algebraic topology, homology stuff, that's pure math that clearly is of no value, right? Math, it's well-known example that there are no possible applications of number theory, right? And so that's what happens. Pure math, it's pure, it's got nothing to do with reality, and then somebody figures out there is a way to use it. And topology is starting to show up. Algebraic geometry is another area that's pretty hot now in data analysis. There are some sources of data. I don't promise you that at all about these, except that LANL is really cool, and you can get the data from Kaggle that I use. And there's a thing in the back with these. And me, technically, I'm not supposed to put my emails on presentations. I'm not entirely sure why, so I do. But there you go. You can get me at either of those, and I think I am done. So, someone has to answer the chat questions, right?
Yeah. No, thank you so much. I guess let's start in the room if anyone has questions or comments.
Is the data that I was dealing with there like humans? For the mouse, the answer is yes. Although I can't promise you it was humans rather than of antivirus software. I believe the Kaggle data was synthesized. The flows data is unlinked. That's a good question. The data that I used, the malicious, was taken on the web. So it's not new data. My colleagues put a honeypot out. A honeypot is a computer that acts like it's really juicy and got some fun stuff on it, so you should hack it. And people send, and it turns out all you need to do to get hacked is to put a Windows computer on the net. But so they collected some things there, but not very many because they didn't keep it up for very long, just a few days. And there's nothing we can really say objectively. One of the things I wanted to do, and I may be doing this year, is put up a more sophisticated, long-standing honeypot. And then, but we are still relying on either antivirus software that tells us tells us it's bad, or the assumption that if somebody puts something on it and it's not me putting it, it must be bad, why else would they do it? Or run the thing and see what happens, which has some problems.
Nobody's asking any questions online yet.
The data sets, can you again summarize what are contained in these different data sets?
Dave was asked to summarize again what was in the data set.
Two data sets that I talked about, two sets of data. There are three sets, actually. There's the flows data, and that is that information about flows between computers. Those are unlabeled, but they tell you things like how many bytes and packets flowed in one direction between these two computers on these two applications, or on this application. And you can tie them up using the ports to figure out what the other direction information is. That's unlabeled, but there are a lot of interesting questions that you can ask about normal data versus abnormal multipliers and things. The cal data is labeled. What it is it's a clone of malware. It turns out, I didn't talk about this in this talk, but it turns out they give it to you in two different ways. They give you for each file, they give you each individual byte, so the value of each byte streamed file, and also decompiled them. So they give you assembly code that came from the decompiler. I didn't use the assembly code for this. On data sets that I provided you, there's a whole range of data. I provide that just for anyone who's interested. There's flow data, and LANL also has some red team data and some various other kinds of data, and it's all documented. They've got some papers and stuff you can look at. Some of the other places provide malware ways, or they provide like the flow data, various networks and things. I would strongly suggest that anything that claims it provides malware, you find out from your organization whether you're allowed to download it, because places don't like that. So at a university, you can probably easily get permission. In a government site, you may be able to get permission but you have hoops to jump through. And in the military, you really have hoops to jump through. But the source data, there is nothing there that can hurt your computer. And that it's perfectly acceptable, perfectly fine.
David, you give a bit more pointers to the algebraic geometry or algebraic topology literature.
Yeah, algebraic topology literature and algebraic geometry literature. The algebraic topology literature, one of the best articles I know of is by Carlson, Carlsson. It's in the bulletin of the American Mathematical Society. I want to say it's 2010. Called in the name of it. So it's easy to find. And in fact, if you Google topological data analysis, there's a lot. There's a couple of books, some good books. One starts with G. I can't remember his name, but he's at UPenn. So if you topological data analysis, GRIST, that's it. GIST. He's got a good book. He's also got a couple of papers. there are a bunch of documents like that. There are a couple of algebraic statistics books there.
It has 2 books.
I have books, but neither of them have either of those. That's where I would look for algebraic statistics. Look at the. Not sure the new things in algebraic geometry for data analytics. I'm not that familiar with, but I've been noticing that there's a lot more people working in that area. So I think that's going to be a hot area pretty soon.
Okay, I'm sorry, some questions here.
Okay.
Okay. So one question from the group, the remote people, thanks especially for your insights on the bytes packet analysis. On your good to be true results, how did you split for cross-validation? I had a similar problem in website classification and condition on site/data source.
For the malware, it was split. In the first case, it was split just randomly 100 into training, and then the other time split it 50-50. It was again randomly. I did not do cross-validation. I did training test because there's 10,000 observations. But when I split it 50, I did split it conditionally, class conditionally. So I split each class in half. But I did that randomly. Each of the 9 classes in half. For the non-malicious was leave one out cross-validated. And so part of that was just because it was my colleague who was doing it, and I said you should do validation. But he's done other things, and so we're not able to break it. So I'm pretty sure that there is a strong effect there.
Another question was, for unlabeled NetFlow data, is there a way to detect beaconing once a host is compromised?
So on what beaconing means, to me, it means that the host that means it's sending out pings, basically, saying I am. And me, because they should be, those have the presumably very few bytes and don't last very long. Also, I think they would be, I don't know how that works. It's been a long time since I've delved into the computer security literature, but I would think they would be sent out on ICMP, which can be broadcast. So it can be sent to a whole network rather than to an individual computer, and that's easy to detect. Another thing you can detect is you can detect bots that are doing a service attack, because you detect flows from many IPs, the same system, that are happening very fast, and they tend to close off. They don't complete any information. So attacks like that you can detect in the flows data.
So it sounds like know your process too, as well as know your data. It's just sort of these features, right?
Yeah. That's the other thing, especially with the malware 9 kind of thing. It's important to know your data. As I said, individual bytes is dumb. There is a reason why it is a good place to start, but it's a good place to end. And so it's important to know the domain when you're doing this. And that's why we knew that results that are too good to be true, because the problem strongly suggests this isn't going to work as well we need to go next step. We needed to understand what's happening here before we went to the next step.
Okay, last question. You specifically talked about supervised learning, unsupervised techniques. My favorite.
Yeah. So,
okay, wait. There's a compound question. In cybersecurity, do we always assume that we have prior classified data as a starting point?
So almost never.
Yeah.
And so there's two aspects of unsupervised learning, in my view, that's applicable to computer security. One is what we call clustering. You want to know what are the natural groups in the data. And there's a whole slew of clustering algorithms. There's streaming clustering algorithms. All of that is cool. I like mixture models, but a lot of different kinds of things there. Outlier detection is the other kind of unsupervised learning. There, the idea is that you kind of want to characterize normal activity so you can determine abnormal activity. But in computer security, it is activity. So you have to assume that the vast majority of it is normal and look for things that don't look like the vast majority of it. Very rarely get a lot of data that has been labeled. Sometimes, and so in the 90s, I did some work with looking at packets and things. There, we had experts that would some of the data saying anything that looks like this is just assumed bad. Anything that looks like this is just assumed bad. The thing that looks kind of weird is because of this, and so it's okay. So we have a bunch of stuff like that. But the vast majority of the data was completely untagged. You just can't look at it, and until it bites you, you don't know it's bad. And so if you see something that doesn't look like anything you've seen recently, you should look at it, and so you should have ways of detecting that. And that's an unsupervised thing. I don't do much unsupervised stuff. Sorry.
That's okay. That's all right. That was the end of the questions. I did suggest that they contact you separately via email, since you put your email there.
Yeah, that's fine. I don't care.
Because there was some responses to your question, and I'm not sure I could them up properly. So you're out there to correspond with Dave.
Yep, and I do read my email and I do respond, although I'm going to be up for a couple of days, so don't be surprised if it's not till next week.
Time for a few more questions, if anyone else. Not? Okay. Thanks for your time. As a small token of our appreciation, you're getting a mug.
And he does drink coffee, I think.
Coffee, yes.
Yeah, and I guess we can give one more round of applause. For those of you that would like to join, we're going to have a reception now at East Street Cafe. So now we're just going to... Yeah, thanks everyone.